Hello everyone, this is Matthew Zenger. Welcome back to our AP Calculus. In today's video, we will cover 0.3 elementary function. Those functions include power function, exponential function, logarithm function, trigonometric function, and inverse trigonometric functions. 0.3.1 Power function. A power function is any function that can be written as fx equal to x to the power of a, where a is a constant. The important idea is that changing the exponent changes the shape of the graph. For example, y equal to x is a straight line, y equal to x squared is a parabola, and y equal to x cubed is a cubic curve. Power functions can also have negative or fractional exponents. For example, y equal to 1 over x has a negative exponent, and its graph has two separate branches because x cannot equal to 0. Another example is y equal to square root x, which is the same as x to the power of 1 over 2. This graph only starts at x equal to 0 because we cannot take the square root of a negative number in real numbers. So overall, power functions all follow the form x to the power of a, but their graphs can look very different depending on the value of the exponent. Now we're moving into exponential function. An exponential function has the form fx equal to a to the power of x, where the base a is positive and not equal to 1. The important difference here is that the variable is in the exponent. For example, in 2 to the power of x, 3 to the power of x, or 10 to the power of x, the exponent is x, which is the variable changing. All exponential function has a domain of all real numbers, which means x can be any value, but the range is only positive numbers, so the graph never touches or crosses the x-axis. On the left, we see exponential growth. As x increases, the graph races faster and faster. A larger base, like 10, grows much faster than a smaller base like 2. On the right, we see exponential decay. These graphs decreases and get closer and closer to 0, but they never actually touches 0. So the key idea is exponential functions either grow very quickly or decay towards 0, depending on the base and the exponent. A very important exponential function is fx equal to e to the power of x. The number e is approximately 2.718, and it is called the natural base. This number shows up a lot in real-life applications, especially when we talk about growth, decay, interest, population, and later in calculus. The graph of e to the power of x has the same basic shape as other exponential growth functions. It passes through the point 0, 1 because any positive base to the power of 0 equals 1. It also passes through 1e because e to the power of 1 equal to e. When x is negative, the values are still positive, but they get closer to 0. So e to the power of x is just a special exponential function, but it is one of the most important ones in advanced math. Before working more with exponential functions, we need to remember some basic exponent rules. First, when we multiple powers with the same base, we add the exponents. Second, when we divide powers with the same base, we subtract the exponents. Third, when a power is raised to another power, we multiply the exponents. The last two rules show how exponents work with multiplications and division. If two terms have the same exponent, we can combine the bases. These rules are important because they help us simplify exponential expressions and solve exponential questions later. Now we're looking at the logarithmic functions. A logarithm is the inverse of an exponential function. So if we have y equal to log ax, that means we're asking what power do we raise a to in order to get x. For example, log 8 equal to 3, because 2 to the power of 3 equal to 8. On a graph, we can see different logarithm functions, like log 2x, log 3x, log 5x, and log 10x. They all passes through the point 1, 0, because any base raised to the power of 0 equals 1. The domain of a logarithmic function is x bigger than 0, because we cannot take the log of 0 or a negative number in real numbers. The graph also gets very close to the y-axis, but it never crosses it. So the main idea is logarithms undo exponential functions. Here we have the relationship between e to the power of x and ln x. The natural logarithm, written as ln x, is just a logarithm with base e, so ln x equal to y means the same thing as e to the power of y equal to x. The graph shows that y equal to e to the power of x and y equal to ln x are inverses of each other. That means they are reflections across the line y equal to x. So when we see ln x, we should think what exponent on e gives me x. Now we have the main rules for natural logarithm. The first rule is the product rule. Ln bx equal to ln b plus ln x. This means multiplication inside the log becomes addition outside the log. The second rule is the quotient rule. Ln b over x equal to ln b minus ln x. Division inside the log becomes subtraction outside the log. The third rule is the reciprocal rule. Ln 1 over x equal to negative ln x. This comes from the quotient rule because 1 divided by x creates a negative log. The fourth rule is the power rule. Ln x to the power of r equal to r times ln x. This means an exponent inside the log can move to the front. These rules are useful because they help us simplify logarithmic expression and solve equations later. This slide shows the inverse relationship between exponential and logarithmic functions. The first rule says a to the power of log ax equal to x. This means if we take a log with base a and then raise a to the result, that we get back to the original x. The second rule says log a to the power of x equal to x. This means the logarithm cancels out the exponential. The same idea works with base e. We have e to the power of ln x equal to x, and ln e to the power of x equal to x. So the key idea is simple. Exponential functions and logarithmic functions undo each other. This is why logs are so important when solving exponential equations. Now we are moving into trigonometric functions. Trigonometric functions describe the relationship between an angle and side length in a right triangle. The three main trig functions are sine, cosine, and tangent. For angle theta, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We also have three reciprocal trig functions, cosecant, secant, and cotangent. These are the reciprocals of sine, cosine, and tangent. Now we extend trig functions from right triangles to the coordinate plane. If we have a point Pxy on a circle, then r is the distance from the origin to the point. Using this, we define sine theta equal y over r, cos theta equal x over r, and tan theta equal y over x. The signs of sine, cosine, and tangent depend on the quadrant. For example, in quadrant 1, all three are positive. In quadrant 2, sine is positive, but cosine and tangent are negative. This helps us find trig values for the angles beyond just right triangles. This is the graph of y equal to sine x. The sine graph is a wave that repeats forever. Its range is from -1 to 1, so the graph never goes above 1 or below -1. The period is 2 pi, which means one full cycle of the graph takes 2 pi units. Sine starts at 0, goes up to 1, back to 0, down to -1, and then returns to 0. This is the graph of y equal to cos x. Cosine also has a range from -1 to 1, and its period is also 2 pi. The main difference is where it starts. Cosine starts at 1 when x equal to 0, then goes down to 0, then -1, then back up. So sine and cosine have the same wave shape, but cosine is shifted compared to sine. This is the graph of y equal to tan x. Unlike sine and cosine, tangent does not stay between -1 and 1. It can go up or down without limit. The dashed vertical lines are asymptote. The graph gets closer and closer of these lines, but it does not touch them. Tangent has a period of pi, so the same pattern repeats every pi units. It crosses the x-axis at values like 0, pi, and -pi. This table shows common values for sine, cosine, and tangent. The most important angles to recognize are 0, 30, 45, 60, and 90 degrees, along with their radian forms. The table also shows how the sign changed for different quadrants. Some tangent values are undefined, like at 90 degrees, because cosine is 0 there. So this table is useful for quickly finding exact trig values. You should pause the video and try to memorize it. And our last function, inverse trigonometric functions. Normally, sine and cosine repeat forever, so they do not pass the horizontal line test. That means they do not have inverses unless we strict their domain. For sine, we use the interval from negative pi over 2 to pi over 2. On this interval, sine passes the horizontal line test, so it can have an inverse. For cosine, we use the interval from 0 to pi. On this interval, cosine is also 1 to 1, so it can have inverse. So the main idea is inverse trig functions only work because we choose a specific interval where the origin of trig function does not repeat. This slide shows the graphs of the three main inverse trigonometric functions. The first one is y equal to inverse sine x, also called arcsine. Its domain is from -1 to 1, and its range is from negative pi over 2 to pi over 2. The second one is y equal to inverse cos x, or arccosine. Its domain is also from -1 to 1, but its range is from 0 to pi. The third one is y equal to inverse tan x, or arctangent. Its domain is all real numbers, and its range is from negative pi over 2 to pi over 2. Remember, every time you see this trig expression, it's inverse, not reciprocal. And that's everything for elementary functions. Please follow for more.